My name is Ville. I used to work at Netflix before founding this company called Outerbounds. And like, yeah, I mean, as David mentioned, like back at Netflix, we started developing this framework called Metaflow. It's open source at metaflow.org. So if you don't want to listen to any of this, I mean, you can just like check out the webpage, and it has plenty of information. And now, yeah, indeed, about a year ago, I left to kind of a startup company around this, and like both at Netflix as well as, of course, at the new company, like we have been thinking about this big question that like what is exactly the modern stack for ML infrastructure, and it's kind of interesting that like bake into that phrase the modern stack. There's a bit of an assumption that there was something before, and maybe there will be something after, maybe a postmodern stack for ML or something of that sorts. And like even more so, I mean, the interesting question that there's the baked-in assumption that that there is some kind of a stack in the first place. And like for those of you who have been following this like a sprawling space of ML ops over the past few years, there's a lot of confusion, a lot of fragmentation. That do we even have a stack? I mean, like, is there a stack that we can use to build machine learning applications? Are there multiple different stacks for different use cases? Or could it be even so that there is the stack that everybody should be using, at least conceptually, to build these applications powered by machine learning that deliver lots of business value? And it is a confusing space indeed. And whenever like I find myself in a confusing situation, that there are like kind of so much going on that it's hard to figure out what even makes sense and what doesn't, I oftentimes look back in history and try to think that, okay, has anything like this happened in the past? And of course, like pretty much always, like when it comes to tech, like we realize that we just keep reinventing the same things over and over again. And I think like when it comes to the question of the stack, like one of the interesting comparison points, at least to me, is that of the web stack. So like if you want to build an e-commerce store, and like imagine like if you wanted to build an e-commerce store back in like during the dot-com boom, I mean like maybe 98 or 99 or so, there used to be this stack. It was really called a stack, and like it was LAMP, and it consisted of Linux as the operating system, Apache web server as your web server, MySQL database, and then like people were really excited about the PHP, the language back in the day. And that was really the stack how people built applications back then. And if you actually like peek under the hood, like what building an application like with the LAMP stack looked like back in the day, you had a diagram like this. I mean, this is actually like from the Wikipedia page, like for the LAMP stack. And I guess the kind of what I want you to pay attention here, especially, is that like you have this like things in the middle, like the storage layer, like there are things like SATA, SAS, SCSI, and so forth. I don't know how many of you even like know what these terms mean, because they don't like seem to make any difference these days anymore. And it's actually fascinating that they also highlighted different file systems like Ext4. There's the process scheduler, like you had the device driver for the network interface card and stuff like that. And then of course, like on top of the operating system, then you had different like open source projects like the Apache web server and so forth, that somehow you tried to kind of run on top of this whole thing. So one thing that's very clear, like looking at this slide, is that it required a lot of technical knowledge, like back in the day, to put together even the most basic website. And like you probably need to have a team of maybe a sysadmin and a database admin, and then like maybe a PHP developer to be able to put even the kind of the most rudimentary site together, not to talk about the payment processing and stuff like that might actually matter for e-commerce. So like obviously, like what happened after a while, I mean actually a long while, 15 years, is that there was this next generation of the stack for web development. It was called the mean stack, like from the MongoDB as the database, Express.js as the web server, and Angular maybe as the front-end framework, and then Node.js as kind of the language runtime. And like one thing that's especially interesting to me here is that if you compare and contrast, if you maybe remember like when MongoDB came out, there was actually like a lot of debate in technical circles whether MongoDB is actually a good product in the first place, because there were many technical arguments that in many ways MongoDB wasn't technically a better product than, let's say, MySQL that people had been using before. But at the same time, MongoDB was resonating like with a huge number of web developers, people building these applications, mainly for the reason that they kind of changed the abstraction a bit. I mean, one thing was that they introduced this idea of a document-based database. So instead of having relations and SQL and all that fancy relational algebra stuff that that had been dominating the database industry for decades, they had this very simple idea that you have a JSON object, and then you can just operate with the JSON object, and everything will be fine. And now, of course, like many technical people felt that, oh, that's horrible. But at the same time, I mean, the level of abstraction like raised to the point that people who hadn't been able to build these database applications in the past suddenly were able to do it. And the same thing with many other components here. I mean, like Express.js, like a higher level than Apache. Of course, like you can see that the operating system at this point actually like it drops from the picture, like kind of it was given. I mean, like Linux was already at the point in time that like, well, things just mainly worked. So you wouldn't have to worry about all those device drivers and whatnot. And also like the language, like, well, I mean, one can argue whether like JavaScript is higher level than PHP, but like things get evolving there as well. And now, like, if you think like what's kind of the state of the art today, like there's this thing called the Jamstack, already introduced 2015, but I think it's only now gaining popularity, where the idea is that like the stack is even simpler. So now, I mean, you're still using JavaScript, but like today, like if you are building, let's say, an e-commerce store, like you don't much have to even like think about databases, definitely not operating systems, not load balancers, and so forth, but maybe you use a platform like Shopify, or like maybe you use some super high-level framework, maybe you deploy a single-page application on Vercel. I mean, just talking to the APIs. And much of that technical complexity underneath is totally hidden from you. So the overall like a trend line, like in all these technical stacks, is that things tend to become more human-centric and less technical over time. And like when I say human-centric, I mean the idea that if you think that like in order to build an application, you kind of have the lower layers, you have to all the way to the hardware and the CPUs. And then like at the top of the thing, I mean, you have the thing that actually like interfaces with other human beings. Maybe it is the actual store. Now we have so much more mental bandwidth to focus on like how do we make the onboarding, how do we make the sign-up flow, how do we make the purchase experience better, and like we don't have to consider the technical details. And that's how things tend to happen over time, like with these technical stacks. And now, like maybe something that's even more exciting is that, that these stacks definitely become simpler, but not only simpler, but also more capable over time. And I guess like the point about simplicity is important, like especially if you contrast that to the idea that the kind of simplicity implies that things used to be more complex in the past and then they become simpler. There's also this kind of somehow there's maybe the intuition that somehow like as things become more advanced, they become more complex. But it's actually fascinating to think that oftentimes it works other way around, that we start with something that's overly complex and has a lot of this accidental complexity, because kind of in the early days of these industries, we simply don't know what we should be doing. Actually, it's kind of rational that like in the early days, like we explore many different directions, we try out all kinds of things, provide technical affordances, and only over time, we learn like what actually makes sense, what is important for the people who build these applications. And then over time, we can shed all this unnecessary complexity from the stack and things become simpler. And at the same time, like we can focus our energies on like providing all these capabilities, like more easy payment processing with Stripe or like whatever it might be. So it's kind of like oftentimes in engineering, we have trade-offs that like we can't get everything. But I mean, like in the case of stacks, I mean, it seems that like we both get things that are simpler as well as more capable. So that's kind of like the mindset, the way how I have been thinking about the stack. And like since the title of this talk is the modern stack for ML infrastructure, I have all reasons to believe that the ML industry is no different, because it's not only the web stacks, but it's also the mobile. It's whatever else you are looking at. I mean, this seems to be almost like a physical law of physics, that like this is how these things tend to go. So there's a reason to believe that like when it comes to building real-world ML applications, things will become simpler and more capable and more human-centric also over time. So now, like what it means in practice is that if you like go back in time, like when I think like the first ML applications that I built a long time ago, like it was kind of maybe using this like a clam stack. Don't Google clam. I mean, it just came up with the name. But the pretty much the idea was back in like early 2000s, or maybe even like before 2000s, that maybe you were in academia building something. The only way how you could actually like say train a model is that first, I mean, there were very few off-the-shelf frameworks available. So most likely you hacked the algorithm by hand, most definitely using some low-level language, unless you were using MATLAB like as an IDE, which was kind of interesting that in many ways it was kind of ahead of its time. But like you would use C, and then like you would also, of course, like a very tightly like work with the operating system, because like the operating systems tended to be a bit still a kind of a like a flakier, rougher at the time, especially when you wanted to do high performance numerical computing. And then like, well, I mean, because so much time was spent on just building the algorithms, I mean, not much time was spent on all the data stuff. So maybe you just use something like Perl or Awk to do the data processing, like just like get the columns from the CSV that you needed. So that was really quite rudimentary back then. And now if you fast forward 20 years, and 20 years kind of a long time, and now like back in 2018, I mean, of course, there's like things have advanced massively. I mean, one of course, the biggest difference is that instead of racking and stacking physical servers, like we can just rely on the cloud, which like frees up massive amount of energy and like kind of a mental bandwidth to focus on other things. So instead of setting up Linux servers, you can just use AWS. And of course, well, this conference is all about data, so I don't even have to say like how much have changed, like when it comes to data processing, the data warehouses, orchestration system, ETL, all that stuff. And like what is maybe even more exciting, like in the ML point of view, is that instead of you having to implement all these algorithms by hand in C, there are these amazingly mature ML frameworks, like of course TensorFlow or PyTorch or XGBoost, scikit-learn, like whatever, what have you. And then you can use a high-level language like Python to kind of get your job done. And then like you can put things together like using Jupyter and so forth. So huge amount of progress over the past 20 years or so. But of course, the interesting question remains that, well, today is 2022, and in a few years, it will be 2025 and so forth. And like most likely the stack will keep evolving. And like if we kind of like follow this linear path about things becoming more human-centric and like even like more capable over time, simpler, the interesting question is that, okay, what's going to happen? Like what will the future look like? And now predicting future is hard. Actually, predicting past is even hard. Like prediction is hard. But one of the best ways to kind of predict the future is to create it. I guess like it was Alan Kay who said that. So now for this talk, I thought that like we can go through this interesting thought exercise that if you were to design an ML infrastructure stack from scratch today, how would you do it? Like what are like those pieces that you think will inevitably be around over the next, let's say, 5 to 10 years? So if we believe in this idea that like in the early days of any industry, like we have a lot of this incidental complexity because we don't know like what we are doing. At this point, maybe we have some idea of the essentials. Like what are those essential components that we know that we can't get rid of and like we want to have as a part of our stack. And now like the first thing that I believe in, and actually like I'd be curious to hear if there's anybody in the audience who doesn't believe in this. I do believe that there will be people around, and not hopefully, I mean, this is not like a climate change or anything that like the people would go extinct, but specifically there will be data scientists around. And actually like this is not just a joke, because there is a kind of a question that if, let's say, the auto ML takes over the world and like the data goes to some system that automatically optimizes everything. I mean, yes, I mean, there's a possible world like where even this guy like won't be around in 10 years. But I mean, let's start with the premise that like we will have data scientists. And if you take any random data scientist today, you look at the person like during the business hours, most likely you will find them on a laptop. And well, now I mean, starting with the very basics, the question is that, okay, so is this going to be the situation in 10 years? Well, now there is the very like a physical interface that most likely like they will be still typing something. I mean, most likely I would even argue that they might be typing code. They might be typing high-level code. Again, I mean, this is a big belief. There are like definitely people who much believe in the no code or even maybe some kind of a low code. But let's say that like especially like Python language is an exceptionally good way for people to express their understanding of the world in a computable form. And I think that will be around. But now the interesting question is that, okay, so they are typing something on the laptop, but what happens then? Like what happens with that code? And now, like for the past 40 years, like we have had this concept of a personal computer. And the personal computer is, of course, quite a revolutionary idea because it meant that you get this personal sandbox where you can experiment with things, you can install things, and you can run things, and like nobody kind of interferes with your stuff randomly. And like in many ways, it is quite empowering and productivity boosting. At the same time, there are like some quite big limitations with that personal computer idea. Like one of them, of course, being that they tend to be on the smaller side. And also like as like ML becomes more and more serious, of course, I guess many companies have have seen over the past many decades is that managing personal computers is kind of a bit of a pain in the butt, and like like in the data governance, in the security point of view, like moving things in a more easily controllable environment like the cloud actually makes life easier. And now when it comes to ML, like besides those like a governance question, there's also the very practical question that because we want to make it very easy to move stuff from prototype to production, it's important that like we minimize any kind of a gap between the prototype and production. And now if you consider that your laptop as of today is maybe a MacBook with the M1 ARM processor, and like your production workloads might be x86 running in the cloud, we know that there are quite concrete differences between the packages you install on your local laptop and the packages you might be using in production. And this is actually like quite specific to ML, because if you are using only high-level languages like JavaScript, you wouldn't have this problem. But in ML, I mean, this is a real deal. And in that sense, also it is beneficial that like you kind of move the actual workloads that you are executing even during prototyping to the cloud. So there's the idea of a cloud workstation, and I think that that's a positive direction. There's of course much work to be done, but like even today you can use VS Code, you can use Jupyter, and it's quite a seamless experience even if you run those kernels on a remote instance. Now the next piece that I think that we won't be able to get rid of, like for the benefit of this conference, is that I think we will always have data. And now there's of course a whole separate track about the modern data stack and like where the data engineering side of the house is going. But let's just assume, like for the purposes of this presentation, that we have some kind of a data warehouse, data lake, someplace where all the business has like the data. So you have the master data record. Maybe it's Databricks, Snowflake, maybe whatever it is. And then the important realization here is that we don't want ML to be an island. We don't want ML to be a separate walled garden that like you have your rest of the business living in some other data warehouse, and then you have your data scientists working in some separate environment, and maybe you can get tiny samples of data in that specific environment. But more and more, it would be beneficial that like everybody like has the same view to the data. Everybody agrees on the definitions of the metrics. Everybody agrees on the kind of the tables. And of course, like we want to enable like people to iterate on quickly, but at least we are kind of living in the same universe of data. And also, it means that the data scientist is more freely able to access like the kind of the actual data sets, not only tiny samples of data. And now, like with this, like comes the big question. Like the other, like a really foundational question is that how do we do compute? And actually, like if you just look at this picture here, that's kind of the holy trinity of what all ML infrastructure is about. I mean, it's some kind of a conglomeration of people, data, and compute. So I mean, like everything we do is kind of somewhere in this triangle of compute, data, and people. And like now the compute, it's actually like a surprisingly multi-dimensional question. I mean, one of the most obvious ways of thinking about this, like a compute layers, is that, well, it allows us to provide scalability. And now, as many of you know, like there are two ways to scale. You can either scale vertically, meaning that you can get bigger and bigger boxes. So let's say you need to load a pandas data frame in memory. It takes 200 gigabytes of RAM. You can actually like get an instance with 200 gigabytes or like 300 gigabytes of RAM from the cloud. And instead of like spending time on optimizing things by hand, you can just get the bigger instance. And actually like that can be very productivity boosting. Now, of course, you can't infinitely scale that way. I mean, at some point you hit the limits. The limits are surprisingly high like today. So that shouldn't be underestimated. But like at some point you hit the limits. So then like the other direction is that you have the horizontal scalability, which is the idea that you can get more of these boxes. And now the beautiful idea with the cloud is that it really affords both types of scalability. You can either get bigger boxes or you can get more boxes, or like some combination of the two. Now, like besides the scalability question, the compute is important because it actually like does even like change the way how we think about the organization, how we think about how people interact with each other. Because if you think like what used to be the situation, like maybe like a long time ago, like maybe with the mainframe, there were only a few people who were even able to go near the computer because it was such a limited, constrained resource. And then at some point we got personal computers, so we could democratize the access to compute. And then maybe at some point, like in late 1990s, early 2000s, maybe your company had like a few racks of servers, cluster running there. And like then maybe you had some kind of a sophisticated job queuing system, prioritization, that like who gets to run like what and when. And the challenge with that idea is that like usually when it comes to experimentation, which is super important for data science, usually the experimental workloads are never like getting a very high priority. And like now you had to kind of carefully dance around that, like who gets to run and what and when. And I think that that's a bit of a thing that like we can kind of start changing our mindset about, like with the cloud. And well, technically, if you assume this idea that cloud provides nearly virtually unlimited scalability, there's no reason why we need to kind of have these like a checks and gatekeepers, like who gets to run stuff. I mean, technically, like we should be able to allow anybody to access these resources very freely. And of course, this would be amazing for experimentation, because now suddenly in this post-scarcity world, like we can actually like try out all kinds of things. We can try like a different ensembles of models, run them in parallel, and so forth. And usually the pushback that I get from companies, like when saying this is of course it costs money, and like, well, maybe Netflix can afford doing it, but I mean like our company can't. And yeah, that's fair. It costs money. And of course the challenge here is that that there's the cost side of the business, and then there's the value side. And now the kind of the simple thinking goes that like, well, if you understand the value of what you are creating, as long as the value of this experimentation is higher than the cost, I mean, then it's a no-brainer. You should still do it. Now the challenge is that most companies don't understand the value of experimentation. It's hard to measure anyways. But the point being that technically the mechanism of letting people access the cloud is at least something that we can enable. And then like based on your understanding of how the value gets created, you can layer policies on like how we kind of allocate the money between teams. And there's a difference between the mechanism and the policy. And that's important to keep in mind. Now, in many ways, this is kind of like a very positive story of liberation. That like we are liberating the data scientists from the confines of the laptop. We are liberating them from having to deal with small data sets, liberating them like from not being able to use compute resources. And there's actually like one more like a point of liberation that I feel is really important, which is that it's a liberation like from the previous job description. So it used to be so that like maybe you had analysts providing insights for the company, maybe you had data scientists producing models, and maybe then like ML engineer building applications, and like you had division of work like that. But now if you draw the comparison like from the kind of the web stack world, what happened over like the past whatever like 20 years like in the web stack is that you used to have teams of sysadmins, DPAs, PHP developers building these applications. And over time we have got to the point that it's only the full stack developer taking care of everything. As a single full stack developer today, you can build end-to-end applications. And it's not because the full stack developers are necessarily like some kind of a magical unicorns knowing everything, including the Linux device drivers today, but it's just that the level of abstraction is higher. And also the kind of the way how we build software is a bit different. Like we are focusing our energies on different points. And like on that note, I do think that this idea of workflows, which is of course like I don't think that it's maybe not new to anyone here. So I mean, like of course, most likely everybody doing data engineering or like kind of a data science knows this idea that you can structure things as a workflow. But the interesting thing as of today is that still many companies, if not most companies, consider that the workflow is something that you kind of slap on top of everything afterwards, after like the data scientist has done their work. So oftentimes what happens is that still as of today, the data scientist, let's say, prototypes something in a notebook or like writes a Python file. And then like afterwards, like somebody slaps a YAML on top of that, like stitching together these individual components, and it goes through a CI/CD system, and then it gets executed. And what it means is that it becomes, of course, incredibly painful to quickly iterate like on the workflow, on the kind of this application itself, because it's somehow external to the whole thing. And it kind of feels that the healthier idea would be to consider that the workflow as the kind of a main deliverable of what the data scientist is working on, which also means that it needs to be an integral part of that local prototyping loop. And now, like with this like a great amount of freedom that like we would like to grant to all the data scientists, machine learning engineers, of course, comes a certain degree of responsibility. And like the responsibility these days like should come in the form of tracking. Like we want to understand the metadata, we want to understand the different versions that get built. And now, as we very well know, I mean, when it comes to machine learning, it's not only about the version of the code, it's also the versioning the data, understanding the lineage of data, understanding the models that get built. And now I would claim that this part is so integral to everything what we do, especially as we start empowering these data scientists to do more by themselves, is that it needs to be an absolutely like a built-in component of the whole system, and not a yet another add-on component that like somehow you have to do as an afterthought, like once you have done everything else. So it kind of becomes, I think Peter like mentioned something in the keynote this morning about this idea of how when you adopt the kind of the culture of experimentation, when you adopt that experimentation mindset, like you also have to be very conscious about the change management and like understanding how things change. And I think that idea of like a tracking like what gets built is very central to this. And of course, like many software engineers know the idea of a GitOps, which is the way how we do it in the software engineering land today. I think that we can do even better in the world of data science. But the end result is that when we put all these things together, like we get this kind of a modern prototyping loop. And the modern prototyping loop doesn't only include the data scientist on their laptop, but it also includes access to the data. It includes access to the compute resources quite freely. It includes the workflow part as well. And of course, like even during the prototyping, we want to keep track of everything and understand what's going on. And now, like since all this is like pretty high level and abstract, I mean, we can make it a bit more concrete by like saying a few words about Metaflow. So now, like Metaflow, ever since the beginning, was kind of built with this mindset, with this vision that this is maybe where the world is going. Now, by no means I'm claiming that this is the only way, or the only implementation, only possible way. So of course, there are many other frameworks and like many other implementations that will show up over time. But I mean, just to make it concrete, let me show how we have been doing it. So for those of you who haven't seen maybe Metaflow before, it's a very, very kind of a simple Python framework by design. We want to get rid of all that incidental complexity. And like it promotes this idea of a workflow to be a first-class concept. I mean, it's not models that data scientists are building, but they're building data science applications of different forms, and like they are being structured as a workflow. So you have a workflow here. You have like, let's say we have two nodes here, start and end. And like correspondingly, we have two methods in the Python code, start and end. They are decorated with the at steps. So we know that those are the nodes in the graph. And then there's the edge between the start and end, which is the self.next transition in the code. So very, very straightforward. Nothing too special about this. Well, now, like what is really nice is that if you want to test your code, I mean, let's say you didn't have the workflow, you were just operating in a Jupyter notebook. Of course, like you would like run the code in the Jupyter notebook. Now that you have the workflow, in the same way, you want to run it locally and see if it works. So in the case of Metaflow, like it gives you this like a very simple command line interface. You can just say Python myflow run, and it executes the workflow locally in the same way as you would do it in a notebook. So you don't have to deploy it anywhere. You don't have to write any separate YAML files and all that stuff. You just test the workflow as the main deliverable of your project. So now the next question is that, okay, about the compute. So the compute, indeed, I mean, it should be a core part of this exercise. So now, as I mentioned, there are two kinds of scalability, and we demonstrate them here. So first is the horizontal scalability. So let's say you want to train 200 models, maybe like kind of a one model per every country in the world or something like that. What you can do is that you can define a Python list, like here, like a self params, and you can do that, okay, I want to do 4 each over the params. And then like what Metaflow does behind the scenes is that it farms out 200 copies of this task to the compute platform of your choice. And now when it comes to vertical scalability, we have the at resources. So you can say that, okay, maybe I'm loading a big data frame, maybe I'm like training a big model or something. So I need like at least 100 gigs of RAM. So I can say that, okay, like I need 128 gigs of RAM like for each one of these boxes. And this is all that the data scientist has to do to be able to inform the system that, okay, I want to do many things in parallel, and like I need big boxes. And then you can just like run the code again locally. I mean, you don't have to do anything more than that. Like, and you can say that, okay, if you know that your engineers are using Kubernetes and like you have set up Kubernetes as the compute layer, you can say run with Kubernetes. And then like the behind the scenes, like we package everything and like submit to the cluster and like all that stuff that needs to happen. Kubernetes is not the only choice. You can use AWS Patch or like maybe in the future like other compute layers. But the key idea here is that like in the data scientist point of view, I mean, it's really pretty seamless. I mean, in some sense, I mean, like if I'm building this code, I kind of don't care at all like how these functions get executed. I just want them to be executed somehow. And like, of course, there are actually a lot of engineering complexity in executing functions at scale and so forth that shouldn't be underestimated. But when I'm in that like a data science mindset, I don't have to worry about that. So then like the other idea is this question of like tracking everything by default. So like now when you execute code in Metaflow, whenever you do self.x, like you assign something to the variables, those things get persisted automatically. So you can actually like go back in time and ask questions about the workflow, that what was the state of or what was the data after executing this step, or like what was the data that was input to my model. Or you can like just see like kind of the compare experiments over experiments and all that stuff. And the key part is that it's not an add-on. I mean, it happens automatically. You don't even have to write extra lines of code to make it happen. And actually, like in the interest of time, I don't want to spend too much time on this question, like how to interface with data warehouses, although it's definitely really an interesting one. But suffice to say that the modern data warehouses like Snowflakes and Databricks and like whatnot, they have the capability of creating materialized views that like you can create, and then like you can download really fast, let's say from S3, allowing you to kind of create these massive ensembles of models really fast without having the data warehouse becoming the bottleneck, or like the data scientist taking down the whole warehouse or anything of that sort. So come and talk to me afterwards if you're interested. So so I think like we have time like for this like a tiny demo, at least for those of you who haven't seen like Metaflow, the latest things that we have done. So I think that this might be fun. So what this shows is that first, like we have a UI that was released just a few months ago. So where you can see what's going on. Like this is just like a basic Metaflow code. I know this is way too fast, so don't worry about details. But the idea is that you can test it locally. You can just like run it as I showed you. And now the whole workflow runs locally. The nice thing is that like if you have this UI installed, you can just like go to the UI, see what's going on, like how long the different tasks are taking and so forth. And a nifty new feature is that now, I mean, with a few lines of Python code, you can also like create these outputs that are understandable to humans. So of course, like the main idea, like with these workflows, is that we are building models, we are processing data, all that stuff. But it is actually tremendously useful that like you can get these like tiny reports that are attached to the execution that you can then see that, okay, what's going on in my models, like built in. And of course, there are many like reporting solutions and model monitoring solutions and so forth. But one of the key problem with many of them is that you have to actually do quite a bit of work in attaching them to do all the executions, both during prototype and production. And then like thanks to all the versioning that Metaflow does behind the scenes, you can just take any version ID and let's say afterwards go to a notebook and ask that, oh, by the way, I mean, that model seemed to be performing well or not. And you can just like see the report card in a notebook. So all these features, the kind of the UI and the cards, they were something that was just like released like towards the end of last year. So even if you have seen Metaflow in the past, these are new features that might be interesting to you as well. So now, just kind of this is big question that like needs to be addressed. That okay, so now we have this amazing prototyping loop. So how do we think about the production? Well, I mean, like what we have learned about production over the past many years, like when it comes to machine learning, is that there isn't a one type of production, but machine learning is kind of becoming like software engineering in the sense that it comes in all shapes and sizes. And like, as you know, you can apply machine learning on the edge. You can have computer vision on the mobile devices. You can have recommendations on a web product like Netflix, or maybe you use a data enrichment. You add predictions to your data stream. So maybe you have some decision support system. And all these are, of course, production use cases. And I think that the most concise definition that we have for production is just like two attributes, what makes production. The attribute number one is that it should work without human supervision. So the idea that like if you somehow have to run something manually all the time, it kind of doesn't quite feel production. So at least it's unsupervised, it's automated. That's an important part of production. And then the second one is that there's a bit of a like assumption that things don't break all the time. So it needs to be highly available. So production means that you are automated and you are highly available. Now you can be highly available and automated in many different contexts. All these cases are production. With this like comes the idea that there isn't like a single way how the data scientist deploys machine learning production. But in fact, there are many different ways. And we, of course, don't want to burden the data scientist in having to think about like every kind or build the kind of every deployment pattern from scratch, which is why we can have these like blueprints for different targets. But what this allows us to do is that it also means that it's so important that like we can integrate to the surrounding production infrastructure for each use case separately. There isn't like a one size fits all way of doing production. Like what works for like Netflix scale recommendations is very different than like what works for the decision support system at the bank or like the edge devices and so forth. Each one of these cases is different. But the key part here is that the prototyping loop in the middle can be quite the same for all of these cases, because these things, compute data, versioning, orchestration, they are quite universal. And then like once you are like happy with your result, you can apply like one of these patterns to kind of deploy stuff to production. And just as a concrete example, what it can mean is that, let's say your company uses one of the like production, like workflow orchestration engines, let's say Airflow or Amazon Step Functions or Argo in production. Now, a key part is that it is highly beneficial that your machine learning workflows run with the same system in the same environment as all the other data pipelines. And the idea that like somehow you have a separate world for data and like separate world for ML and like separate for like production system, it actually like it's a sign of incidental complexity, which is exactly the thing that we want to get rid of. So in the case of Metaflow, we have these adapters, so you can deploy, let's say, that you can do step functions create, you can deploy it to step functions, or actually like Argo and Airflow are features that are coming later this spring. And now equally important part here is that this is not the one-way street. It's not something that you deploy as a kind of a waterfall. But when things fail in production, like you need to be able to come back and then reproduce those issues and fix them, and then like deploy the fixed version back. And this is actually something that's surprisingly often missing in our production systems, that we know, let's say with CI/CD, how we deploy the production, but no one ever thinks how we come back from production. Meaning that then like in the production, we slap all kind of observability tools and we slap all kinds of alerting tools that if something goes wrong, at least we know. But oftentimes it's an afterthought to think that, okay, so how do we actually fix these problems as quickly as possible? Because the definition of high availability is not only that things never fail, it also means that when things fail, as they inevitably fail, how can you fix things as quickly as possible? And that's why, for instance, like we have this resume feature, like how you can resume even any production execution locally in an isolated environment, doesn't step on the toes of anything in production, and fix those issues and then go back. Then another like important aspect of production is that it never ends. Like it's kind of fascinating fact about of course like all software, but I mean machine learning in particular, that like if you manage to build something that creates value, nobody ever wants to take that down. It becomes this eternal like organism that never dies, and like you only want to improve it. And like so you kind of get into this like a cycle that you have both the prototyping loop and then you have this like a constant iteration on the production things. And oftentimes like the way how you want to improve these like production systems is that, let's say somebody creates a new version and then you deploy it, but you just don't overwrite the main production version, but you deploy it side by side with the production, and then maybe you conduct some kind of an A/B experiment and you want to test like whether the new thing is better than the old thing. Because as many of you who do ML very well know, I mean, it's really hard to say in advance if model A is better than model B without actually like seeing how they behave in practice. And I think also this is very much the reality, like where we are already living today and increasing will be living in the future, that in contrast to software engineering, like where we can at least test things and get some idea if it works or not, like as a binary thing, increasingly like we can't know if these systems work without deploying them all the way to production, but not overriding things dumbly, but I mean, just running things side by side. And in order to be able to do this, I mean, of course, the whole setup needs to support this idea of having these isolated whole like sequences of workflows that can run side by side. And again, I mean, like so many companies that I see today and I talk to today, I mean, they are like at the point where they can barely deploy one thing. And then when I ask them that, okay, I mean, what if somebody else wants to test the new version and like run it side by side? They're just shaking their head and like that. No, I mean, like we wouldn't ever dare to do anything like that, which is kind of sad, because that's how you actually start constantly improving things. And then like finally, like kind of after like we are done with all this, like we get to the parts that are somehow feel that are very, very much to the core of data science. I mean, this is the part like where the data scientist, and this is kind of the part like why we need the data scientist in the loop, because this is how you actually map your domain knowledge about the world like to the system. So there's of course the whole like the movement about data-centric AI, which means that, okay, when it comes to, let's say, feature engineering, which again like comes in many shapes and sizes, how you do feature engineering for computer vision is very different how you do it for relational data, which is very different how you do it for streaming data or semi-structured data. But this is the place where you actually map your domain knowledge like to the system. many ways how you can do that. And then finally, you slap the model on top of the kind of the created data sets and the features. And again, I mean, depending on the use case, you can use all kinds of frameworks. And of course, I mean, this is a fast-moving field. The key idea, like with this whole modern ML infrastructure stack, is that we can allow data scientists to have almost a maximal amount of freedom at the top of the stack. Like we want them to map their domain knowledge in the form of models. We want them to map their domain knowledge in the form of features. But then like when you have these like a foundational features, like how you access data from the data warehouse, compute, orchestration, versioning, it's something that the framework, the platform can take care of you. And like those are kind of a non-negotiable. So you have to have versioning, you have to have compute, you have to have data. But then like how you like implement these things, much more freedom at the top of the chart. And then like also we believe that like the key idea, like how you build, how anybody should be thinking about these modern stacks, whether it's machine learning or like web stack, is that you want to provide a coherent experience so that you get rid of that incidental complexity. The incidental complexity, let's say in the early web stacks, came from the fact that you had a separate operating system and you had a separate database and you had a separate like a language and so forth. And like none of these things actually like worked seamlessly together. And like you were constantly fighting at the seams of the systems. And the same thing, of course, like happens today with the ML infrastructure. You have different parts and they don't quite fit together and it's complicated and like things are like flaky. And like building these coherent ideas is of course like not easy, and you don't want to reinvent everything. You don't want to reinvent every wheel in the world. Like you can integrate with the existing systems, but at least at the user interface layer, like you want to have a coherent user experience. So this is my belief, like where the world will be going. Again, I mean, like definitely there will be many implementations on the right-hand side. I mean, kind of hopefully, of course, like one of them will be Metaflow. But I mean, definitely, if you are building like internal frameworks or like if you are building commercial products, I mean, definitely like try to project based on like everything we have seen in the past where things are going. And like just as like a shameless plug, I've been writing about this stuff in a book because I always run out of time. And so you can go and buy the book. So the profits like from the book go to good causes. So like even if the book is worthless, at least the money goes for a good cause. And also we have a Slack as everybody else, so please join. Thank you.